Today we shall consider the Turing machine as a acceptor. Okay, we have considered the Turing machine as an input output device. We will see how it can accept a language. So, in this case the Turing machine, say M is taken as a 7 tuple k sigma gamma delta q naught blank f. So, 7 tuple, sometimes it is given as a 6 tuple, that blank is not given separately, where k is the set of states, sigma is the set of input symbols, or it is the input alphabet, gamma is the tape alphabet, and sigma is contained in gamma, q naught is the initial state, f contained in k is the set of final states. The blank symbol belongs to gamma, is the blank symbol, it is the blank symbol. The symbol denoting the blank, and delta is the mapping, delta it is a mapping from k into gamma into k into gamma into LR. Now, we are considering a deterministic machine, deterministic Turing machine. If it is non-deterministic, it will be k into gamma into finite subsets of k into gamma into LR, right. So, in a formal way, we denote the Turing machine by these 7 tuple with set of states, set of tape alphabet, portion of it is the input alphabet, q naught is the initial state, f contained in k is the set of final states, and one symbol in gamma is denoted as the blank symbol, and delta is a mapping from k into gamma into k into gamma into LR. That is, the mappings are given in this form, delta of QA is equal to PA LRR. That means, if it is in state Q reading the symbol A, it can go to state P, rewrite over A, the capital A, and move left or right. An ID, or the instantaneous description, is a string of the form alpha 1 q alpha 2. See, when you consider it as an acceptance device, the left end is fixed and the right end is infinite. The input is initially given here, padded up with blanks. For accepting, the Turing machine can write over the blank cells and use as many cells as it wants. So, the ID is described as a string. Suppose the non-blank portion contains something like A1, x1, x2, some xm, the non-blank portion. See, you must remember that in between it may print a blank also, right. So, but whatever follows this is blank on the tape. This is the leftmost symbol, right, the leftmost symbol, and this the non-blank portion followed by many blanks, infinite number of blanks to the right. If this is the situation and the head is reading the excite symbol in state q, head is pointing to this symbol and the state is q. The ID is written as x1 x2 xi minus 1 q xi xm. This is the ID. This is a string alpha 1, this is the string alpha 2. So, alpha 1 and alpha 2 they belong to gamma star, q belongs to K. So, the idea of the Turing machine or the instantaneous description is given by a string, right, which denotes the non-blank portion. The head position is marked here. Qxi means the head is pointing to xi and the state is q, right. Okay. Now, suppose this is an ID, this is the ID, current ID, and you have the mapping delta of q xi is equal to say p some a r. It is a right move, delta of q xi, that is it reading xi, it is going to state p, rewriting this as a and going to state p, and it is going to read a next symbol, that is the next ID. Then from this ID, the next ID is written with the symbol, the next ID is x1 x2 xi minus 1, xi has been replaced by a, the next symbol is p and it is reading xi plus 1, head is reading xi plus 1 and this will be the next ID. Okay. If it is a left move, delta of q of xi is p a l, the left move. From this ID, it will go to the ID x1 up to xi minus 2. Now, this will left move means it will go here, right, in state p. So, p xi minus 1 a xi plus 1 xi. This is the next ID. Is it clear? It cannot move left of the end. So, you cannot have if it tries delta of some q x1 is equal to some p a l, this is not allowed. It has to stop that, it will halt, right. And what will be the initial ID? Initially the input is given here. So, initial ID will be q naught w. If w is the input, then the initial ID will be q naught w, right. This is the initial ID. Without loss of generality, you can assume that once it reaches a final state, it halts. The machine, once it accepts, it halts. There is no loss of generality in assuming that you can do that. So, at the end, there will be some configuration alpha 1 q of alpha 2. It will halt with some such ID, where qf is a final state. Okay. The language accepted is denoted by L of m or T of m. L of m is the set of strings of the form W, W belongs to sigma star, and the initial ID is Q naught W. Of course, what does that symbol and then star means? If you get in one step, you use this. This is as usual is the reflexive transitive closure. If you get in many steps, you use the star. So, Q naught W is some alpha 1 QF alpha 2, where QF belongs to F, alpha 1 alpha 2, they are strings over gamma star. So, if it is reading this, it can read this symbol, it can read here. Suppose it is here in state Q, this is the non-blank portion, say some alpha. After some time, initially what is given is the input, after some time some non-blank portion is there, and the first blank symbol it is reading in Q, this is alpha say, then the ID will be alpha Q. It is a alpha 2 is empty, epsilon, alpha 2 is epsilon, alpha 1 is alpha. Now, it can print something here and move right, or it will just, there is another way. Suppose the last symbol is some x, it is here in Q. So, the ID is this, ID is alpha Q, this is alpha say, alpha x is the content of the tape, it is reading the last symbol x in state Q. Now, suppose it prints a blank and moves left, then the alpha whatever the symbol is there, it will be like this, alpha 1 A is alpha, it will be reading this. So, alpha 1 A is alpha, the last symbol of alpha is A. Same thing only, how it is manipulated towards the end, I am just mentioning. So, the language accepted is given by this. Now, the way the definition is given, there is no condition that it should read the whole input. It is not at all given that it should read the whole input, okay. But for particular languages, when you design the Turing machine, when you construct the Turing machine, you always make sure that the whole input is read. Let us construct a simple example, a power n, b power n, how it will accept a power n, b power n, n greater. This can be accepted by a push down automaton, but not by a finite state automaton. So, as a Turing machine, how will you accept it? This is the one example where I will write the whole moves in completely. Later on informally we will describe, this can be written something and so on. So, formal writing the delta move will take lot of time, because it is not difficult, but it takes time. So, this example will write all the mappings. The idea is like this, the input is given like this, A, we suppose I am taking a particular example, followed by blanks. Please note that this is different from the B. Now, this has to be accepted. The machine is started in state Q naught reading a leftmost symbol. What it does, it changes this into x, goes here, changes the B into a y, comes back, changes this a into x, goes back, changes this into a y, comes back, changes this into a x, then goes back, changes this into a y, then while coming back it sees that there are no more a's, it also sees, goes and checks that it is not, there are no more B's remaining, it sees the blank symbol, it will accept, right. So, how do you write the mappings? This is what you start with. So, delta of Q naught A is equal to Q1 X R. So, first move A is changed into X and you move right. Now, in Q1 it moves right, it has to move right and it has to see the B. When it sees the B, it will change state and start moving to the left. So, delta of Q1A is Q1A right, just moves right, and delta of Q1B, when it sees this B in state Q1, it makes it into a Y and starts moving left. So, in state Q2 it starts moving left. So, delta of Q2A is Q2A L, it starts moving like that, and then when it sees the X in state Q2, it has to start the process all over again. So, it moves right in state Q naught. Delta of Q2 X is Q2 Q0 X R. So, it moves right in state Q naught, the whole thing will be repeated again. So, in Q naught when it sees a, it will change this into a X and move right in state Q1. In Q1 when it sees a, it will move right. I am sorry, this has been changed into Y, okay, I did not mark that. Now, in Q1 it looks for a B, right, it has to pass through the Y also. So, delta of Q1 Y is Q1 Y R. So, when it comes here, it will replace this by a Y and move left in state Q2, it will come up to this point. When it sees this X, it will move right in state Q naught, another pass is over, right. Now, again the same thing, it will change this into a X, go to state Q1, and in Q1 it will pass through all this thing and reach here in state Q1. In Q1 when it sees a B, it will change that into a Y and come back, it will come back here in Q naught, Q2 and then move right in state Q naught. Now, in Q naught it is supposed to see a to start the next pass, but it is seeing a, what it is seeing? It is seeing a Y, that means it has exhausted all A's. So, delta of Q naught Y is, it goes to another state Q3 Y R. Now, it must see that there are no more B's remaining. So, in Q3 it just passes over the Y's. So, delta of Q3 Y is Q3 Y R, and in delta in Q3 if it sees a blank, it will halt. Q4 it will go to Q4, you can say Q4 and halt, and Q4 is the final state, F is Q4 is the final state. So, for Q4 no moves are defined, when it goes to Q4 it halts, right. Now, what will happen if you have more A's or more B's? Suppose I have one more A, what will happen? It will come here in state Q naught, replace this by a X, and it will move in state Q1 looking for a B, and in Q1 it will see a blank. The move is not defined for that, Q1 blank. So, when it reaches here in Q1, it has to halt, no move is specified, it has to halt, but it will not accept that. What will happen if you have more B's? Suppose I have one more B here, so 3 passes are over, and you see here this y in Q naught. So, it will go to Q3 and start moving, right. So, in Q3 it can pass through over the y's, but if it sees a B, if it sees a blank it will halt and accept, it will go to Q4 and accept. If it sees a B, no move is specified, isn't it, it has to halt, but it not accept the input. So, here the acceptance, you can see that it has to see the first blank symbol and then only accept. That way we are making sure that it is seeing the whole input. By the definition it is not necessary. So, what happens if something is accepted without going through the whole input, after seeing this portion it accepts, say, what does that mean? It could be there are some symbols, not blanks. That means anything followed sigma star, that into sigma star, any string will be accepted, that is the mean. But for all examples you make sure that the whole input is read and it sees the first blank symbol, leftmost blank symbol, and then only accepts. Now, we have already seen the Turing machine as input output device. When you consider it as input output, usually you are not bothered about the left hand being fixed, okay. That is not really, the tape you can take as infinite. Initially when you start it will be input will be given, and when you end whatever is given is the output. You can look at it as computing some functions, computing some functions. They are called Turing computable functions. So, for example, you can be given x with a separator and y, and you may end up with x plus y, answer x plus y. So, ultimately this is the input, and ultimately you end up with x plus y on the tape. This is possible. So, it is performing the operation of addition, it could perform the operation of multiplication. So, you may end up with x y on the tape. Now, if the numbers x and y are represented in unary, it is very simple. You have to just remove that hash symbol, shift them, shift all the symbols one position, it will be over. Addition will be performed like that. If it is binary, you can do in some other manner. But anyway, we have seen that converting from one base to another base is not a very big problem. We can always, we are not talking about efficiency, how much time it is going to take at this stage. Later on we will talk about that also, but at this stage we are only thinking about how the function is computed, not really how many steps it takes to compute. Because unary means something will be easy, but conversion from unary to decimal, decimal to unary, all those things will take time, right. Then multiplication again you can do. Then x power y, x and given x and y, how to compute x power y, all those things can be done. So, any function I am looking at them as natural numbers to natural numbers or some 2-3 arguments of natural numbers computing some function. Okay, anything for which you can write a program for that matter, you can compute with the Turing machine. So, these are called Turing computable functions. So, now as I mentioned, anything for which you can write a program you can do with the Turing machine, and when you learn programming you learn certain techniques, how to write a do loop, how to write a repeat until loop, how to all those things, when where you have to use the loop, where you have to use if then else construction and so on. Similarly, there are techniques for Turing machine constructions. So, we will see, I will not write the mappings one by one, but I will informally describe the techniques. Techniques for Turing machine construction. One is storage in finite control. What is finite control? It is state really. So, some amount of information you can store in the state. So, what does that mean? The state itself you have to take as a tuple, 3 tuple, 4 tuple or something like that, then you can store some information in that. Of course, that has to be finite. You cannot, the state can be taken as a 2 tuple or a 5 tuple or something like that. That has to be finite. You cannot have keep on increasing that. For example, suppose I want to accept a b power n or b that is first symbol should not be repeated again, or it can be over another alphabet also, ABC you can take, first symbol should not occur afterwards. Okay. So, if it is like that, in the store when it reads the A, the tape will contain something like this, left end will be, you can start here, ABB, it has to accept such a language. So, when it reads this A, the state becomes QA, it shows that it has read the A in the state, then it can move, and at any time this should not match with this. Okay. Like that you can have. Another thing is, suppose I want to accept W, C, W, W is a string of A's and B's. So, what we can do is left hand I can fix. Suppose A B B, C A B B. No, this is not context free. This is context sensitive. It is not context free. You cannot have a push down automaton accepting that. Now, the idea is it can read this, change this into X, and store that information as QA, so that it remembers that it has read A, and after moving through C, the first symbol it has to the first symbol has to be the same A. If it is not, it will stop rejecting, otherwise it also changes this into X, comes back. Now when it sees this B, it can change this into Y, but store that B in the state, then go back. After the C, it will leave out the X's, then the first symbol has to be again a B, it will change that into a X, come back, then when it reads this, change, store that B in the component and so on. So it can store some amount of information in the state, and that technique is called storage in finite control. Then you can have multiple tracks. The tape, so far we are considering only one tape. We are assuming that the Turing machine has got only one tape, right. In fact, multi-tape Turing machines are there. You can have multiple tapes for the Turing machine, finite number of tapes. But at present we are considering only one tape, but this tape can have multiple tracks. Any tape can have multiple tracks. So for example, it can be like this, it may be divided into say 3 or 4, something like this. There is only one tape and so only one head. If it is multi-tape, for each tape there will be a tape head. Here there is only one tape and this head is pointing to this one, and suppose I have say ABC here, in essence it means, what does that mean? Gamma itself is taken as a triple, the symbol, this is a symbol of gamma. Here we have taken the first one, storage in finite control. What we have done is we have taken the state as a tuple, and only one component will be really the state, the rest of them is used to store some information. Here multiple track means the tape symbol, sometimes it is, instead of using so many symbols, it is convenient to use it as a tuple. If you want to change the middle one alone, you can do it. Suppose there are ABC 3 symbols, in 3 places there will be 27 symbols. No? Instead of using A1, A2, A2, A27, I use it as a triple. It is convenient where you are going to change, and this technique is really useful because sometimes what you do is you may have something on the first track, you want to do something and then check whether at the end you get the same thing as the first one. For example, I want to this is one, and I want to see whether this grammar, this string is accepted by the grammar, what we consider S goes to A, S B, or S goes to B, or something like that. So what you do is, in another track you start with S, then start with this, right, start again replacing this and so on. So finally when you end up with terminals, is it matching with that, you can check. Okay. So some sort of a calculation or computation we can use for the second and the third one, and then the input, compare with the input and so on. In essence, multiple tracks means the tape alphabet is taken as a tuple, that is all, and this will be useful in many cases. Okay. Shifting of symbols. Again I will take the example of a grammar. I want to simulate, I want to check whether something is AB, ABB is derivable using the grammar. S goes to ASS, S goes to. So, I start with S in the second track, replace it by ASS. Now, I want to change this into a B, I can do that. Now, this S I have to replace by ASS. For this, I have to shift here actually it is all blank, so it is not very difficult. I will take this string, this is more okay. I will take this string, it will illustrate in a better manner. So, S has been replaced by S. Now, this S has to be written as ASS. For this I have to shift the S. This S cannot be written as ASS because there is no space here. So, I have to move this 2 places and then rewrite S. So, sometimes I may have to create some space. So, how do you do this? As a mapping, the delta mapping, how will you do this? Again, suppose I want some tape contains x1 to xi plus 1, xm. Now, I want to create 2 blank places here and shift from xi to this portion. I want to shift 2 places to the right, so that I can do something here. So, what I do not know the length of this fixed length. If it is fixed length, you can do in one way, but I do not know how long it is going to be, but whole thing I want to shift 2 places so that I can write something. So, what you do is you take the state as a tuple, 3 tuple, triple, and then when you read this, store this xi here, move right. When you read the xi plus 1, store the xi plus 1 here and move the xi to the third, from second to third component you move. Then next you will be seeing xi plus 2. When you see xi plus 2, in an automatic manner you store xi plus 2 in the second component, move this to the third component and deposit this xi here. Systematically you can do that. Then next step, xi plus 3 will be there, that you store here, move this to the third component and whatever is there you deposit here. That way you can shift everything to 2 places to the right. And when you do the initially when you store this, you create 2 blank positions here, 2 blank portions you create, and later on you use it for some purpose, right. So, this is shifting towards the right, you can also shift towards the left. Checking of symbols. What does that mean? The same example which I considered, WCW. Suppose I have AB, B, AB, C, AB, B, AB, followed by blanks. I said you can store some information in the state, that is necessary again, but change everything into X and so on. So, I am losing the information. You can use X and Y and then also you can some information you can keep. Another way of doing it, I do not want to do anything with this. I want to keep them as ABB, AB, etc. I do not want to do anything. Then have 2 tracks. The tape you have 2 tracks. What you do is start from here, mark it off, and that it has read one A, you remember, in the state. Then move past this, then the first symbol, check it off. Again come back, and when you come here, check the symbols you leave out, unchecked symbols, first unchecked symbol you have to see. It is a B, store that information that it is a B on the state, move to the right, check this off, then move to the right and check this off. So, what essentially you are doing is, which symbol you are matching, that you are storing in the state. A has to match with A, B has to match. But whichever symbols you have marked, you have matched, you check, you put a tick mark and check. Finally, you make sure that everything has been checked, right. So, this is, you are using 2 tracks. The second track is putting a tick mark that you have checked that symbol. State also you are taking as a tuple, and some information you are storing in the state. This is another technique. Subroutines. This is a technique which you usually do in programming. The same technique you can follow for Turing machines also. One Turing machine can be considered as a subroutine for another Turing machine. For example, if you want to multiply 2 numbers m and n given in unary, m into n, 5 into 3 to end up with 15. So, what do? You make a copy of it. Answer I want here. Numbers are given in, if they are given in binary, you can convert them into unary first or something like that. So, 2 unary numbers are given, I want to multiply them. So, in the end I have to end up with 15 once, right. So, first the thing is, you check this off for, and then copy this here, then check this off, copy this here, check this off, copy this here, and so on. You will end up with, later on you can erase this portion. Okay. So, what are the things which you are doing? You are copying. So, copying one portion here, this you are doing several times. Each time when you check off a symbol here, right. So, for copying alone you can write a Turing machine. You can write the mappings for delta mappings for copying one string here. Then the main one, it will check off a symbol and then copy this, right. So, copy will be called 5 times in this example, right. Now, what are the things which you have to take care of when you write a subroutine? Generally when you have a program, what do? Subroutine will return a value and so on. So, here the state's main Turing machine is T, subroutine is T1. The states should be disjoint. right. The states of this and the states of this, they should be disjoint. They should obvious, is it? And then when you want to call the subroutine T1, from here the delta mapping should take you to the initial state of this. If you go to the initial state of this, that means you are calling the subroutine. So when you reach a final state here, you must get back to one of the states here. So return to the value. Okay. So a main routine and subroutine. You can also have this subroutine calling another subroutine T2 and so on. Just as in programming, main routine can call a subroutine, that subroutine can call another subroutine and so on. Again the same things, the states have to be disjoint, and from the initial state you have to look into the other details. So these are some techniques for Turing machine construction. One more example, suppose I want to compute a function m minus n, this is proper subtraction. So another how do you compute this? Input is given as 0 power m 1 0 power n, this is the input. You should end up with 0 power mn if m is greater than or n, blank tape. How can you do this? Suppose I have this blank tape, this is blank. So what you can do is change this into a blank, go here, change this into a 1, come back, change this into a blank, go and change this into a 1, come back and change this into a blank. Now looking ahead, you see that there are no more zeros. So what you do is you make all of them blank, come back here and here you print a 0. You will end up with 2 zeros. Now if you have less, for example if you have less, you should end up with a blank tape. What will you do? Change this into a blank, then go and change this into a 1, change this into a blank, go and change this into a 1. Now when you are moving left, you find that no more zeros are left. So erase everything, you end up with a blank tape. So each problem you have to look at in a separate way and decide what is the procedure to be followed. Now the language accepted by a Turing machine is called a recursively enumerable set. or RE. It is equivalent to type 0 languages, type 0 languages. in the Chomsky hierarchy, finite sets are included in regular and regular sets are included in CFL, is not it? And CFL is included in CSL, context sensitive language or type 1, and RA is outside this. Now, here comes deterministic CFL. It is higher than regular, but less than CFL. Languages accepted by deterministic push down automata. Now, we have seen about acceptance by a Turing machine, but if a string is not accepted, then the Turing machine may go to a state from where it can go to a stage where it will not be able to proceed further, and it is not a final state, that is possible. Or in Turing machine there is another thing possible, it may get into a loop. For example, it does not accept an input. So, after reading, this is the input followed by blanks. After doing something, it starts doing the same thing again and again, it gets into a loop and it does not go to a final state, none of the states is final. So, maybe it is writing or just reading, it may move left and right or just a few symbols and do the same thing again and again, and none of the states is a final state. So, this string cannot be accepted by the Turing machine, right, but the machine does not halt. So, for accepting it has to halt and accept. For accepting a string, a Turing machine has to stop, it has to halt and accept. For rejecting a string, it may go to a position where it will not be able to make further moves. So, it halts in a non-final state, if you have to say it in that way, or it can get into a loop, right. This is a very important point you have to note. Now, a set accepted by a Turing machine which halts on all inputs is called a recursive set. A language accepted by a Turing machine which halts on all inputs is called a recursive set. So, recursive sets are higher than this, they correspond to Turing machines which halt on all inputs. I told you when earlier that there is a small difference between a procedure and a algorithm. A procedure corresponds to this. If the answer is yes, it will give the answer, but if the answer is no, it may get into a loop, it may go on trying and it may never end up. Whereas an algorithm corresponds to a recursive set, that is, an algorithm always halts and tell you an answer yes or no. Okay. So, when you say decidable, told you given a context free grammar, is it ambiguous or not? You cannot give an algorithm for that. That is called an undecidable problem. We shall study about that in our next 1 or 2 classes. So, that means you cannot write an algorithm for that. Okay. Even if you are able to write a, procedure, it is still undecidable. If you are not able to give an algorithm, it is undecidable, right. Ultimately you must say yes or no, and the problems generally decision problems, and optimization problems. Decision problems are, the answer is yes or no. Does the graph have a Hamiltonian circuit, or the travelling salesman problem, does it have a path solution, that is yes or no. Find the one which has the least cost or something like that, that is an optimization problem. So, you can look at the problems are optimization problem or decision problems, mainly we will be considering only about decision problems, yes or no answer. Of course, you can look at an optimization problem as a decision problem by converting it in a little bit slight different way, but generally we are more concerned with decision problems, right. And the one problem which we will study, two of them we will study in detail. One is the post correspondence problem, and another is the Cook's theorem, that is Boolean satisfiability is NP component. Both we will see how the idea of Turing machine is used there. So, we shall consider more generalizations of Turing machines and restricted versions of Turing machines later in the next class.